Hello, this is Professor McKinsey. I wanted to look at one of the ideas in section 2.5 from Beckman of using percent tables to solve various percentage sorts of problems. And I think I want to talk about this just from looking through a few examples to illustrate the main ideas. So, first example, suppose we wanted to compute 15% of 84. So the idea of a percent table is to set up a table with two columns. In one column we would have various percentages indicated, and in the second column we would have the corresponding parts of 84. So for example, we could start with 100% corresponding to 84, since 100% of 84 is 84. And what we're going to do from here is rescale by multiplying or dividing each row to build new rows, and in hopes, in this case, of being able to figure out what 15% of 84 would be. So as a start, we might be tempted to divide both sides by 10. And if 100% of 84 is 84, dividing by 10, we would find that 10% of 84 is 8.4. Now, keeping in mind that we're trying to build 15%, we could take this last result with 10% and divide it by 2, and find then that 5%, which is half of 10%, is equal to 4.2, or half of 8.4. So we divide it by 10, and then we divide it by 2, and we have in our table what 10% of 84 is, what 5% of 84 is. Finally, we can finish the problem by observing that 15% would be the sum of 5% and 10%. And so that then means that 15% of 84 should be 8.4 plus 4.2, which gives us 12.6. And so our answer would be that 15% of 84 is equal to 12.6. Now, presumably, that's the same answer you would get if you had done this one of the other ways that we know. If we had taken 84 and multiplied it by 0.15, presumably you end up with 12.6. Or if we had set up proportions, 15 over 100 equals x over 84, and solved that algebraically, you would probably end up, you would expect to end up with 12.6 using either of those methods as well. But part of the advantage of using the table, the percentage table, is that it's a relatively easy thing to do. It's fairly intuitive, and for many people it corresponds to how they might compute percentages in their head, just doing the calculation directly without having to get into complicated algebra or decimal arithmetic. The next example I'm going to look at, computing 12% of 55. Again, we would start with a table with 100% of 55 being 55. So our first row would have 100% and 55. We're going to rescale things, trying to get 12% here. And so one way you might think of doing that, if we divide by 10, we would have 10% would be 55 divided by 10, or 5.5. And we're looking for just a little bit more than that to get up to 12%. And so there are a couple ways we could go from here. We might divide by 10 again and have that 1% is 0.55. And then to get 2%, we would just double that. We can multiply by 2. And so 2% would be 2 times 0.55, which turns out to be 1.1. Actually, as I'm looking at this now, it occurs to me that we could have skipped that middle step and just gone from 10% down to 2% by dividing by 5. And that's maybe would have been tempting, because 5.5 is easy to divide by 5, and of course gets you at 1.1. So part of the moral, I guess, is that there's more than one path we can take in constructing these tables. And now we have everything we need to finish the task. 12% is 10% plus 2%. And so if we add together the results we found for 10%, 5.5, and 2%, 1.1, their sum is 6.6. And so it should be the case that 12% of 55 is equal to 6.6. Another example, where things are moved around a little bit. Suppose we know that 15% of some number is equal to 84. We want to find the original number. Again, we can do this in a number of ways, but using a percentage table, we could start with our first row having a correspondence between 15% and 84. And we're going to use the same sorts of manipulations of multiplying or dividing both entries in one row to build a new row. And now our goal is to figure out what 100% would correspond to if we know that 15% goes with 84. So one way to proceed would be to start by dividing by 3. That's a relatively easy calculation to do, and it would tell us what 5% of the original number is, because 15% divided by 3 is 5%. 84 divided by 3 turns out to be 28, and so 5% of our number is 28. If we double that, we'll find that 10% of our number is 2 times 28, which is 56. And now we can multiply by 10 and have that 100% of the original unknown number is 560. And so here's a technique of using a percentage table to solve a missing quantity number. If we know that 15% of some numbers is meant to be 84, it turns out the number which has that property is 560. One last example of where here now we don't know the percentage, we simply know the two numbers involved. So what percent of 80 is equal to 7? Here we're working with percentages or portions of 80, and so we could start our percentage table by observing that 100% of 80 is just 80. And again, we're going to do the same types of manipulations, but now we're trying to construct the number 7 in the right-hand column, where at the moment all we have is the number 80 instead. And again, there's probably more than one way to do this, but the first thought that occurs to me in trying to get down to 7, it would be really convenient if we could build like the number 1 in the right-hand column. And so kind of working in that direction, I'm tempted to divide both sides by 8 here. So if you divide 100 by 8, you get 12.5%, and 80 divided by 8 is equal to 10. If we divide both sides of that by 10, we might find that 1.25% is equal to 1. Now we're trying to build the number 7 in the right-hand column, and if we know that 12.5% corresponds to 10, dividing that by 2, dividing it in half, would give us 5 in the right-hand column, and half of 12.5% would be 6.25%. So we can build the number 5 at 6.25%. To get 7, I'd want to add 2 to that, and you might think that might then suggest that we could take the previous line and multiply by 2. And so 2 times 1.25 is 2.5%. 2.5% of 80 is 2. 6.25% of 80 is 5. And so to build the number 7, I would just add those last two lines together, and we'd find that 8.75% in our table corresponds to 5 plus 2. It corresponds to 7. And so it turns out, based on this work, that 7 is 8.75% of 80. So I hope you found this helpful. This is a quick run-through of a few examples of using percentage tables to solve percentage problems from section 2.5 of Beckman.